So, we are going to start our discussion today with the foundations of the atomic theory. How did we come about with the discovery of the atom? We're going to do that early on. Then second period, we are going to talk about the structure of an actual atom. So we're going to start off here with atoms, the building blocks of matter. We're going to go through a kind of like similar to a timeline talking about, we're going to start with Democritus and build up on different discoveries of the atom and hit off with some key points. So these are some pretty heavy hitters when it comes to the atomic theory that we're going to talk about that you probably should know and know the important things about these people. Now, when I click this first slide with Democritus, I don't think it's really that necessary to know what years he lived. Actually, I don't even have it for him. But early on, very early on, as early as 400 BC, Democritus said that there was a basic particle that everything was built on. And he called this basic particle the atom. Why did he call it the atom? Well, the Greek word that means indivisible is atomos. Atomos means indivisible. So Democritus said there's some basic building block that everything is made of. You can't divide it. It's the smallest thing possible. So we are going to call that the atom. I don't think you need your periodic tables just yet. We're probably going to need them later on. So some foundations that we're going to build on of the atomic theory. In the late 1700s, it was accepted that an element was a substance that cannot be further broken down by ordinary chemical means. Elements will combine to form compounds, and those compounds have different physical and chemical properties than the atoms that they were formed from. They cannot be further broken down. They combine to form compounds. And those compounds that are formed have different physical and chemical properties. Now, we're going to take a gander here. Here is a chemical reaction. The chemical reaction is involving sodium reacting with chlorine to form sodium chloride. I'm sure we've all heard of sodium chloride, haven't we? It's salt. It's table salt. Now, sodium, chlorine. What do we know about those two things? We're going to check this out right here. Here is a video that we're going to watch of sodium reacting with water. Okay? Now, let's watch that again. That happened pretty quick. So that's sodium right there reacting with water. That reaction, yeah, I mean, it wasn't, you could see there was the reaction with water, a little fireball spinning around there, right? Definitely, if that reacted with water, would you want to put that in your mouth with that little fireball and that little poof at the end? I don't think so. Might be what? Yeah, I'm not putting that in my mouth. All right. So, sodium reacting with water. Okay. Chlorine gas. Chlorine gas. Anybody know where chlorine gas kind of got its bad rap? World War I. Okay, what'd they call it? Not tear gas. Mustard gas, because chlorine has a yellowish color. Okay? Now, what you might not be able to read that I'll tell you that says chlorine gas. Number one, more effective than other types of gas because it is deadlier. The gas canisters can be thrown or shot from land or dropped by planes. The gas billow out of the canisters in big green clouds. So, we've got this substance that created that little fireball when it was reacting with water. We got this deadly gas. But when we mix those two together and they make a compound, we put it on our French fries and eat it. So the properties individually are drastically different than the properties together. So just because this has sodium right here and this has chlorine does not mean that the properties are similar to each of the atoms' individual properties. So we put them together, and there we have it, the salt. The law of conservation of mass. Law of conservation of mass. Those of you that have taken IPS probably dealt a great deal with the law of conservation of mass, which states that mass is neither created nor is it destroyed during an ordinary chemical reaction. So the mass that you have before, the mass with the reactants, must equal the mass with the products. Mass is not created nor is it destroyed. So if we look at this particular example, we have the production of carbon dioxide, carbon reacting with oxygen. As you can see, if you add up the the reactants, carbon, oxygen, the reactants, carbon's 12, oxygen 16, but there's two of them, so we got 12 and 32. When you put that together, seems to me that that equals 44. All right, look at the product side, carbon dioxide. Each carbon 16, there's two of them. Each oxygen is 16, there's two of them. Each carbon is 12. Okay, once again, 16 and 16 is 32 plus 12 is 44. the law of conservation of mass. Mass is neither created nor is it destroyed. The law of definite proportions is another foundation of the atomic theory. The law of definite proportions states that a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample or the source of the compound. So my little picture here, okay, my little picture down here. Here's my reactants. There are my products. This is the blue spheres are oxygen. The yellow ones are hydrogen. So right here, we have two molecules of hydrogen reacting with a molecule of oxygen to give us two molecules of water. So those are two molecules of water. The law of definite proportions state that no matter how much water you have, you still have two hydrogens bonded to one oxygen. So whether you have a drop of water, still H2O, or you have a pool full of water, it's H2O. So the law of definite proportions, that there will be two hydrogens bonded with one oxygen, doesn't matter the size. The law of multiple proportions. The law of multiple proportions state that if two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers. So, what is that getting at? Well, let's look at these two compounds. The one on the left is sulfur dioxide. The one on the right is sulfur trioxide. They are composed of the same two elements, sulfur and oxygen. So the simplest whole number ratios, this is going to be 2 oxygens to 1 sulfur on the left, 3 oxygens to 1 sulfur on the right. So 2-to-1 ratio, a 3-to-1 ratio. The law of multiple proportions. Now, a lot of this information here on Dalton is not really essential to have in your notes, but John Dalton, 1766-1844, was an English school teacher. Not that he taught English, he was from England, all right? So Dalton had a proposal explaining the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And he summed up his atomic theory with 5 statements. And the 5 statements that Dalton has is the stuff that you need to focus on here. So, John Dalton, Dalton's atomic theory. That, first of all matter is composed of extremely small particles that are called atoms. He stole that probably from Democritus. Okay? That all matter is composed of atoms. He stated that atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. So based on this statement, Dalton said that all oxygen atoms are identical in size, mass, and properties. Said an oxygen atom in Seatown, Ohio is the same as an oxygen atom in London. However, oxygen atoms are different than carbon atoms. So atoms of different elements are different in size, mass, and properties. Dalton's third statement said that atoms cannot be subdivided, they cannot be created, they cannot be destroyed. Also, atoms of different elements combine in simple whole number ratios to form compounds. And when those compounds are formed during chemical reactions, the atoms are combined, they are separated, or they are simply rearranged. So, Dalton had these 5 statements that built his atomic theory. Now, does that mean that Dalton was correct? We're going to see that other people built on Dalton's ideas, but at that time, everything Dalton was saying seemed legitimate. Well, that was until a gentleman named J.J. Thomson, Joseph John Thomson, discovered the electron. That's B-I-G to remember. J.J. Thomson, electron. He discovered the electron. Thomson proposed what he called the plum pudding atom. And the plum pudding atom consists of negatively charged electrons stuck into a positive lump of protons. So these negatively charged electrons were clumped into these positively charged protons. Thomson's model did not include neutrons because they were not yet discovered. We did not know about neutrons yet. So his plum pudding atom just dealt with protons and electrons. Now the thing about J.J. Thomson's plum pudding atom is I don't know what plum pudding is. Okay? I can't visualize plum pudding. It doesn't seem like something that I would like because I don't like plums. However, when I show you this picture here, all right, here is the model in which this whole big sphere here is the positively charged area, and these little negatives are the electrons that are in the positively charged areas. Now, what I see when I look at that, I think of tapioca pudding. You ever had tapioca? It's got those little clumps in the pudding. That helps me visualize the plum pudding method because I don't know what plum pudding is. I know what tapioca is. I like that. So those little negatives are the electrons that are in that vast sphere of positively charged areas. Ernest Rutherford then came along. Ernest Rutherford came along, and he proposed the nuclear atom. He proposed that there was a dense nucleus that was surrounded by electrons. So there's a dense nucleus in the middle that's surrounded by those electrons. Further experiments revealed that the nuclei of atoms were composed of protons and neutrons. So Rutherford discovered the nucleus, and upon further experimentation, it was thought that the nucleus had protons as well as neutrons. Now, with Rutherford comes the gold foil experiment. The gold foil experiment. This is how Rutherford discovered the nucleus. All right? He had an alpha particle emitter right here. And he shot alpha particles into this gold foil and had this little screen that would detect the alpha particles. Now, sometimes the alpha particles went straight through the gold foil and hit the screen back here. But as you can see, other times the alpha particles hit something and bounced back, or were deflected to other areas. That led Rutherford to believe, hey, there is something that is pretty dense in that gold foil, because when my alpha particles hit it, they bounce off of it. So there's something in there that's dense, causing those particles to bounce off and be deflected. The gold foil experiment, Ernest Rutherford. Niels Bohr. Niels Bohr, always one of my favorite. Chemistry is boring, and they spell it Bohring. Little chem humor. Chemistry is boring. Niels Bohr. Niels Bohr, 1885-1962, proposed that electrons are arranged into circular paths that he called orbits around the nucleus. So he said that these electrons follow a path around the nucleus, and he called that path orbits. Well, what does that sound like? What does that sound like? Things following circular orbits around something else. The planets, right? Well, he called that his planetary model, because he said that these electrons orbit the nucleus much like our planets are orbiting around the sun. So Niels Bohr came up with the planetary model of the atom.